So let's have a look then at merger simulation. So the idea is, well, we have a market described by price competition, differentiated goods. We are interested in the effects of a merger. We have a practical merger that we have to assess. Why not just compute what are the price rises that occur as a result of this merger? So in order to do that, what do we need? Well, we need the demand functions, we need the marginal costs, and if we have those, we can compute the first order conditions, solve those both pre-merger and post-merger. So we have Nash equilibriums in both cases. Compare those two, look at whether prices increase, and if they increase by too much, we should be worried and do something about it. And if prices remain more or less the same, then no big worries here. So let's do that. So what would we have to do? Well, start with estimating demand, right? So we cannot just take demand for granted, so we have to look at the real world data. So we might have information on prices and quantities. So we need to estimate demand function from that. So a typical way of estimating demand is trying to estimate constant elasticity demand, basically meaning regressing the log of the quantities over time on the log of prices. And you know that this beta parameter here will in this case exactly measure, well, the derivative of log of quantities with respect to log of prices, which is the elasticity, right? That's what elasticity essentially is. So beta here measures what market elasticity is, and that's precisely what we would like to know. Well, there's a little bit of a catch here, so you should not just use OLS if you will measure these, if you estimate these equations, because you know that in these price demand models where price and demand are set by matching supply with demand, you will suffer from some endogeneity. So this means in practice that this epsilon term here will be correlated typically with the price term here. So that means that your OLS estimate of this beta will be biased. So you can't have that, you don't want that. So you need to do something about that. And what you typically do in order to circumvent that problem is you will instrument this P. So you use instrumental variables to avoid to get rid of those complications of the fact that epsilon itself will be correlated with price. But of course it's doable, and once you have done that, you will have some estimate of your demand elasticity. And well, we can go on and then compute, use it as our input to the demand model. Of course, in reality, we do not just have one product, but we have multiple products, because we are looking at a merger of firms which produce different differentiated products. So we need to actually take care of actually these cross-price elasticities, which means that we now have n different products. So Qi will be, this I index here will range from 1 to n if there's n different product versions. So we'll have quantities for each of these products, for each t, for each day if you wish, or each month, each time step that we have, which will depend on some alpha I, and here the beta ij will basically consist of all those own price but also cross price elasticities of demand, and again there will be these epsilons over here. So why not just estimate that? Well, it will mean estimating all these beta ij's. So how many are those? Well, if both I and j run from 1 to n over these different products, well, we have n squared cross elasticities. Is that a problem? Well, typically yes. So typically these markets, if we're interested in, have not just 1 or 2 or 3 or 4 products, but perhaps even 1,000. So we're going to look at a particular merger, the Unilever Sara Lee merger from 2010, which involved the deodorant products they both produced. And that involved more or less 1,000 products. So 1,000 because you have different brands, lots of different brands in this market. And also for each individual brand there might be different package sizes and different packages that are competing actually with each other. So all in all, it turned out the n is of the order of 1,000. What does that mean for this beta, a number of cross elasticities? Well, they will be n squared of those, so about 1 million cross elasticity that we need to estimate. Well, that's getting to be pretty elaborate, right? So it's going to be hard actually to make consistent estimates for 1 million different parameters and to use those. So we need lots and lots of data. Well, we have much data, but not that much. So you have to do something, and what people do is to create a demand system with a little bit more structure, so a little bit more constraints basically on what this demand looks like, in order to be able to actually estimate this reliably. So one version of a demand equation that is sort of more manageable, which is actually used in some form or other, is logic demand. So we're going to look at logic demand in case of this particular merger that I just mentioned. So the Sara Lee and Unilever merger, in which Sara Lee produces before the merger the Sanex product, and Unilever actually had a lot of different products like Axe and Dove and Rexona, so products that you might know from your local supermarket. So what this additional structure is that's used in this particular decision, so for this particular merger, and I'm going to urge you to have a look actually at the technical appendix of this merger decision, because this technical appendix is essentially a paper in its own right describing exactly the approach here, the econometric and quantitative approach that was taken into doing this merger simulation, so in estimating the price increases from this merger. So have a look at that. What they use, if you read this paper, this technical appendix, you see that they use logit demand form, so something which is actually quite common in this business. So what is logit demand? Basically posits that consumers will experience some utility which depends on the brand that they buy. So there's some fixed effects for each of these brands, packages. So J runs over these products here. It will depend on price by some parameter alpha, which is going to be the same for all the different products. There's going to be some product effects based on characteristics like basically the size of the package or the type of product, basically in the larger group that this product is in, plus some idiosyncratic effects, error effects pertaining to this particular consumer. So each consumer will observe all the different brands, and then will pick that brand, that product J, which gives him or her the highest utility. Well, if you compute this and what the effects would be of their equilibrium choices, and if you in addition to that add some assumptions on the distribution of those error terms, particularly have some extreme value type of distribution here, what this would lead to is that market shares will be described by this particular logit formula. So the market share for some product J turns out then to depend on e to the power the u for product J, and by that I mean these first three parts here for product J, which only depends on the product, not on the consumer, divided by 1 plus the sum over all these e to the power u of all the other products, and then product J itself is included in the result. So the sum over all the different products of this e to the u case. So this is a particularly convenient form for market shares. And it's going to be much easier to estimate the relevant parameters, because what are those parameters? Well, there are these alphas over here, and there are these betas over here, and that's a small number of parameters typically. So let's do that. Let's do the computation. You have to know what you're doing econometrically, but once you've done that, you will have figured out what those alphas and betas are, and you might be able to actually figure out then what the elasticities are. So what would these elasticities look like? It turns out in this particular type of model, own price elasticities, and you can check this by actually looking at the derivative of Sj with respect to Pj, and then multiplying by Pj and dividing by Sj. And if you do that, you'll find out that that gives you the own price elasticity. You'll find out that that will take precisely this form: minus alpha times the price. It only depends on price, on this alpha parameter, and on the market share for this particular product. And likewise, the cross price elasticity, so the cross price elasticity between product J and product K, where those two products are different products now, will again depend on this alpha parameter. So again, that's this price, this parameter, and multiplying price here, coefficient multiplying price in the utility functions, times the price of product K times the market share of product K. So that's easy, but actually this has a slight disadvantage. So it's very restrictive, so we don't have much to estimate. So in particular, you see, it depends mostly on, only in this case, on the alpha and on the that we are measuring, that we're estimating, plus on the prices and the market shares that we observe ex ante. So that makes it easy, but it's too restrictive, because what you see here is, typically we have, as I mentioned, lots of products, or perhaps 1,000 products. So the individual market shares for each of these products tends to be small, which means that 1 minus Sj tends to be very close to 1 for each of these products. So what that means is that the own price elasticities in this particular model turn out to be mostly determined by alpha times the price itself of this product. Or in other words, the own price elasticity is completely proportional to price. Is that realistic? Well, perhaps a little bit, but not completely. It's rejected actually to be the only driver actually of own price elasticities. So this is one disadvantage. Gives elasticities which only depend on the price of the product, whereas in reality we do see different kinds of own price elasticities and not only proportional to prices. Second disadvantage is, if you look at the cross price elasticities, which govern the substitution patterns between these different products, you see that those cross price elasticities are completely proportional to the market share of the product that you will shift your attention to if you go away from your first product. So if product J increases in price, you will shift away your attention to other products. But on average here, what happens is that this shift occurs by and large in proportion to the market share, the ex-ante market share of all those products, of all those other products. So what that means is, if you turn back to this example of deodorants, so if Dove for women, for example, increases in price, so it will mean fewer people will actually buy this particular product. They will instead buy something else, a substitute. According to this equation, what will they most likely buy? So where's the demand, the cross price elasticity largest? Well, to those products which have the largest market share. Well, that turns out to be X for men. So what this model by itself posits is that if we raise prices for Dove, most of the people who do no longer buy Dove will actually turn to buy X for men. So Dove for women buyers will go to buy instead X for men. Well, that's perhaps not what we have in mind or to expect for those buyers. So we are missing something here. So this is too restrictive. We have to expand this model a little bit to allow for slightly different substitution patterns across these products that are more in accordance with reality. So how would you do that? So how did the competition directorate of the European Commission do this? Well, they use a nested logit model. So basically what that means, they use a two-level nested logit model. What happens is that ex ante, so before doing the estimation, they posit that we can actually divide up all these different products into different subcategories. So the first category here, the nests, is going to be making this distinction between deodorants aimed at men, so male deodorants, versus deodorants aimed at women, which for some reason are called the non-male deodorants in this decision. So have a look at that. It's not my terminology. So that's the first nest, the first category. Then in addition, it's a two-level nested logit model. So there's a subnest, a second level here, the subnest. So within each of these categories, the male and versus the non-male deodorants, we also make a distinction between those which are particularly advertised as being skin friendly versus those which are not necessarily, don't have that as their primary quality. So this allows for a subcategorization of these different products. What do we do with these nests or with these different categories? Well, we are going to allow or to posit that there's going to be a certain correlation structure on those error terms in the utility function that's consistent basically with these different categories. So we're going to allow correlation between products within one category, so within one nest or within one subnest, to be different from the correlation pattern between products that are in different nests. So that's what we posit. Then we can measure instead of estimate. Well, what are in practice those the parameter for these correlations? What is that in practice if you do the econometric estimation? And then you can test whether this ex ante stated correlation that we expected, whether that in practice when we do the estimation, whether that turns out to be significant. And turned out to be significant is the choice of making this distinction turned out to be significant in this particular instance of this deodorant market. It means that still within these nests, so within the male skin-friendly products, there is still this proportional substitution that we talked about, but no longer among different nests. So what would that then have as an effect? So here actually is a result, a table from this particular from this paper. So let's look what this means. So you see different brands that are available in the Netherlands. So for instance, X here is one of those brands. So let's see how we can read this table. So in the first column over here, we see that if the price for X goes up and therefore fewer people buy this X deodorant, so let's say of every 100 people that are lost to the X brand, so would no longer buy this X product, what would they buy instead? And basically that's called the diversion ratios. So what will they buy instead? Well, most of them actually will turn to the Rexona product. 22 of those 100 that we lose on X will go to Rexona. A lot of them also will go to these other brands over here. And very few of them actually will go to Dove, and very few will go to Sanex. If instead we look at Dove, so what happens if we raise the price for the Dove product and people will go away from buying the Dove brand and instead buy something else. So what will they buy? Well, the majority of those will buy, for instance, Sanex, Rexona, but actually none of those will actually buy the X product that we earlier identified. And same diversion ratios here are computed for these other products. So you see in particular that there's a strong relation, basically a strong substitution between, well, in this case, for instance, Dove and Sanex, but no strong substitution pattern between Dove and X. So somehow Dove and Sanex are more closely related in this competitive setting than Dove and X are. Okay, so that's the demand structure that we now have estimated in in this nested logit form. So once we have done that, we want to go ahead with our program of computing what price increases. Well, we do not only need what the demand is for these products, but we also need input on what are the marginal costs. So we need the marginal costs for these for each of these products, and then we know the demands. We can then compute the Nash equilibrium before the merger, so prices before merger, and the prices after merger, and we can compare those. So how can we measure those marginal costs? Well, one way of looking at marginal costs is, well, perhaps you can use accounting data, right? They have lots of numbers there, but typically those numbers are not very reflective of marginal costs. They are sort of full costs with all kinds of fixed components that are allocated in some more or less arbitrary way to different brands. So typically that gives us a pretty bad insight in what are the actual marginal costs. So the approach that is most often followed in this area is, well, let's look at the equilibrium that we see today. So before the merger, you can see what the quantities are. We can see what the prices are. Let's assume that before the merger, these firms are indeed following a Bertrand-Nash strategy. So they are solving their first order condition today in their current form without having merged yet. And somehow the prices that we observe today will then be their optimum Nash equilibrium prices. Does this help us? Yeah, well, because that does help us, because that tells us that the first order conditions for each of the products today before the merger should be valid, right? So for each of these products, we can observe what are their QIs, quantity that are sold. We can observe the prices that we see today in the shops. We know from our demand estimation what the cross price elasticity, these DQDPs are. So we know everything basically in this equation. The zero first order condition should be 0. The only thing that we do not know is what are all those CJs, right? We do not know, we want to know what are marginal costs. Well, if we know everything else, we can basically invert the system. So this is just a linear system for all these marginal costs for all the product J. We can invert that to compute what are the marginal costs for each product J that are consistent with these first order equations. So that's basically what's done in this exercise, also in this deodorant paper. So have a look at that. So now we're there, right? We have demand, the whole demand function. So this particular logi demand with this nested structure. We have the marginal cost because we just computed those from the pre-merger data. Now we can go on and predict, compute again, simulate what's going to happen if we bring two of these companies together and join their products into one portfolio. So that's what we're going to do. We're going to look at what's the effect of the change in ownership. So we're going to make sure that we will have now one merged company which combines all the products that used to be in company 1, say Sara Lee, and in company 2, those products of Unilever's. And then again solve the first order condition, but now with this different set of products within each firm, particularly in this merged firm, we'll have the combination of all those previously separate products and see what the new equilibrium is. So that will allow us to find post-merger prices. And then we're done, right? Almost. We have to then compare post-merger prices with those pre-merger prices that we had before. So that's what the Commission did, and here's a table that comes from this paper. You can find this in the paper as well, where you see actually the changes in prices. So change in prices for the X brand, for instance, is pretty small. Actually, if you look at the various geographic markets, Belgium, Spain, Netherlands, UK, with changes in prices for both Dove and the Sanix brand, which were produced by these two different companies that were going together, and which also turned out to be, from this demand estimation, to be close competitors. Well, indeed, there you see that there is a large price effect of this merger. So from 10% increases in Belgium and the Netherlands for the Dove brand to over 20% here in the Netherlands and the UK, and almost 20% in Belgium for this Sanix brand. So that gave rise to some concerns for the Commission, particularly in this domain. And indeed, well, what the Commission ultimately decided, as you can read in this merger decision, is that the merger was clear, so it was allowed, but subject to the divestment of, indeed, particularly this Sanix brand to some independent, to some other company. So that without this Sanix brand, actually, these price changes were not that worrisome. As a last remark here, you could actually also use this simulation model to carry out the SNP test. And there's a little paragraph in the paper that actually deals with that. So remember what the SNP test was, the small but significant non-transitory increase in prices test. It was a test to determine what's the relevant market for these products. So what that you have to do, well, you have to assume hypothetically that all products in your hypothetical product market will be combined into one portfolio served by one monopolist. Compute whether prices, by doing so, will go up by more or less than 5%, and that's going to give you information on whether indeed these products together form one relevant market or form multiple sit in multiple relevant markets. And then indeed the researchers in this case, they actually did that exercise and indeed found that the relevant market here was not the market for all deodorants, but male and non-male markets per country were separate relevant markets. So have a look at that as well. Okay, so that was an actual case, the deodorant case. This merger simulation was used by the Commission. So the next bit will be a paper by Bjørnestad and Verboven, where actually they again do some merger simulation exercise, but now on a merger that was allowed. And what Bjørnestad and Verboven decided to do was to check whether those assumptions that we would have made before the merger to analyze, to assess the competitive effects of this merger, so these price increases. If we look at this merger which was allowed ex post, so after a couple of years after the merger was actually carried out, do we see those price effects that we predicted ex ante? Do we see those realized ex post? So we'll have a look at that paper in the next video.